Hello, Physics Nation. My name is Nate Larmond. I'd like to do a workbook problem from 5C, Impulse. A truck has a mass of m and initially moves with a speed of v naught. Consider the two cases. The truck makes a gentle stop, and the truck makes an emergency stop. All right, I'd like to start with the middle diagram. Force is on the y-axis, time is along the x-axis. So these are really common ways to find impulse. Oh, if the velocity is positive and the truck ends up stopping, that means the impulse has to be negative. The force has to be backwards. So that's sort of trick number one. The force is negative, and so we are below the x-axis. That's a gentle stop. Oh, hang on. No, that's an emergency stop. That's a short period of time. Sorry. A gentle stop would be a small force over a long period of time. So there you go. That's negative F delta T. Here, what did I do? 2 by 6, I think? Or maybe 2 by 7. Anyway, the difference is we have a big negative force over a small period of time. This is emergency braking right here. But we have the same change in momentum. Same truck, same incoming velocity. I don't really understand why College Board describes these as bar graphs. Like usually bar graphs are for qualitative data, like discrete groups, like corn plants, soy plants, I don't know, pumpkins. But like if you have a scale along the x-axis, it's quantitative data. So we should be plotting points here. Anyway, like their point is the incoming positive momentum is perfectly canceled by the negative impulse, so that you have nothing leaving. The truck is at rest. Same incoming positive momentum, same negative momentum. It's just this is, I don't know, negative 2 newtons over 7 seconds, and this is negative 7 newtons over 2 seconds. In both cases, the change in momentum is the same. A times B is B times A, but it matters a lot in terms of, our delicate biological systems. Rapid accelerations can rupture the pipes in your body. That's usually how people die in car crashes. It's not the broken bones that kill you, it's the internal bleeding. All the delicate, arteries, veins, and capillaries break, and your heart keeps beating, and you bleed internally. So, it's good that College Board is using car crashes to illustrate momentum. Their clients are a very at-risk population. The second part B, asks to do a ranking task. The car company wants to sort of rate the time it takes for these barriers to stop different sorts of collisions. So the simplifying assumption is the force that is applied in all of these cases is the same. So we're trying to rank the time it takes to stop them. The longest time is on the left, the shortest time is on the right. And of course, they want a justification in a few coherent sentences. The time is proportional to the incoming momentum. If they're heavier, they're going to take longer time. And if they're going faster, they're going to take longer time. So really, we're just ranking which one has the biggest incoming momentum. That's proportional to the required time to stop these vehicles. So, pretty simple. It's just a momentum ranking. Okay, here's my handwritten version. Income positive momentum gets canceled by negative impulse, leading to no final momentum. A little force applied over a long period of time can cause the same change in momentum as a big force over a short period of time. Hewitt used to draw really big variables, so we have big force, little time, little force, big time. 100 newtons applied over a quick period of time causes the same change in momentum as a small force applied over a long period of time. And the point of the graphs is really just to rearrange the impulse and momentum theorem. Impulse causes a change in momentum. Okay, well, how about we add the initial momentum? The initial momentum plus the impulse, that is the change in momentum, causes the final momentum. And as I wrote, a lot of computer models use this very basic iterative process to predict the next step. The initial state plus the change equals the final state. Old plus change equals new. And here's the numerical version of the second part. So like I said, we're just ranking incoming momentum. 10 meters per second, 3,000 kilos, 30,000 kilogram meters per second. Twice as fast, but 100 kilos is like a dirt bike or something, 220 pounds. I'm not even sure you can get a vehicle that's 220 pounds. Anyway, that's only 2,000 kilogram meters per second. 30 meters per second is really fast, but now we're down to 1,000 kilos. That's a very light vehicle. But it still has 30,000 kilogram meters per second. So, they love to throw in equivalents in these ranking tasks. So they want to make sure you know how to rank them even when there are two that are the same. And then D is going fast, 20 meters per second, and is pretty massive, 2,000 kilos. So this has the greatest incoming momenta, 40,000 kilogram meters per second. We're just doing a momentum ranking because the momentum is proportional to the time required to stop it. So the time for D is greater than the time for C, which equals the time for A, which is greater than the time for B. Let's see. Because the retarding force is constant, the time is directly proportional to the change in momentum. So the stopping time ranking is really a ranking of the incoming momentum. Right, and here I just rearranged the impulse and momentum theorem. Let's see, throw in negative for the force, 0 for the final momentum. So we get delta T equals the momentum divided by the force. And this is a constant. Thanks for watching. See you in the next video.